All right, everybody. So we're going to start with our graphing now for our trig functions. So we're going to be graphing sine and cosine today in section 6.3. So we're going to be graphing these two equations. So y equals sine of x, and then y equals cosine of x. So a couple quick things to remember when we do this, when we graph. The input, our domain variable, is the x, and our x values in all of these are going to stand for the angle measurement that we are having. So sine of 30, cosine of 45 degrees, sine of 5 pi over 6 in radians. So this can be in either degrees or radians. Doesn't matter, although I think you'll find most people are going to be a lot more confident and comfortable graphing in radians, ultimately, because in radians, once around the circle 2 pi, that's the same as 360 degrees. 2 pi, though, is only a number a little bit over 6, which is a lot smaller and a lot easier to deal with than if you're thinking about going all the way out 0 to 360. For scale purposes, a lot of people prefer radians. Our output, then, what does our y value stand for? Well, y in this is the ratio that we get when we do sine or cosine of that angle measurement. So remember, trig functions are ratios of two sides in a right triangle. So when we're actually talking about these outputs, these range values, they are the ratios of those two sides in that triangle. So the value that we're getting out for y is always going to be whatever that SOHCAHTOA ratio was in that triangle with that value. All right, so we're going to graph these two new paragraphs. So we're going to go back and do what we've always done to graph a paragraph. We're going to go ahead and make a big XY table, and we're going to fill in the values, and we're going to plot points. So I'm going to be having you do some of this on your own here. So I'm going to have you pause the video. So if you take a look at the table on the next, pause it after I tell you what to do. I'm going to have you kind of rough here starting off on a Monday morning. I'm going to have you go ahead and fill in this table. So we have sine and cosine, and I put the angle measurements in radians. It might be easier for you, and I'm going to start at 0. So it might be easier for you to think in degrees. If it is, go ahead and just fill in if that's easier. So pi over 4 is 45, pi over 2 is 90, 135, and so on. If that's, excuse me, easier for you to do, think the degree measure, but I need you to fill in the sine and cosine values for those, each of those. So I'm going to go through the first couple with you and then have you fill in the chart, and then we'll kind of check in and see how you're doing. So at 0 degrees, sine is 0 and cosine is 1. At 45 degrees, both sine and cosine are root 2 over 2. So we're just thinking our unit circle here, special values. I made the selection to do 0, 45, 90. We don't need to do all the 30s and all the 60s and all of that as well. You don't have to do every single point. We're just going to get enough that we can see what the picture is. By the way, we will never graph this many points again to be able to see what they are. We just need to have enough points so you can see the picture. Let's see, 90 degrees, sine is 1, cosine is 0, and so on. 135, sine and cosine, it's a 45-degree reference angle, so they're both square root of 2 over 2. But 135, 3 pi over 4 is in quadrant 2, so cosine would be negative. So I'm just going to have you continue and fill in the rest of the table for those values. You can use your pink sheet if you need to. Hopefully you remember what these values are. Now for practical purposes, we have to graph these. So square root of 2 over 2 doesn't make a whole lot of sense to people because where is that? So think about what that would be as a decimal. So square root of 2 over 2, just go ahead and type it in your calculator. So square root of 2 divided by 2, see what you get. I think that's about 0.71 in that ballpark. So whenever we graph that, that's what we're going to be thinking of. So go ahead and pause the video and fill in the rest of these values. Negative angles, remember, just mean you're going in the opposite direction. So negative 45 or negative pi over 4 means the same thing as 315. So negative pi over 4 is the same thing as positive 7 pi over 4. So your answers for both of those I just starred should be the same. So go ahead, pause, fill it in, then we'll compare. All right, so here's what I ended up with for each of these. So if you take a look, hopefully you ended up with the same thing. And remember, every time you see square root of 2 over 2, when we're actually practically speaking, graphing these, then we're going to go ahead and write that as a decimal so we can plot those points. So these are just our special values, and I selected these because I thought they would be quick and easy for us to deal with. All right, so we're going to go ahead and graph these two. So on the first one, I'm going to go ahead and have you label y equals sine of x so we know which one we're doing here. All right, and we're going to plot the points. So what I'm going to have you do is look at the sine column on your table, and we're going to go ahead and plot these. So sine at negative 2 pi, that was 0, and then we had square root of 2 over 2, and then 1, square root of 2 over 2, 0, negative square root of 2 over 2, negative 1, negative square root of 2 over 2, 0. Now, one thing to notice about how I had the axes here, I probably should have labeled this first. When you look at the picture the way I have it, the x value, remember our x-axis, those were angles. I'm actually going to write that. The y-axis was the ratio. So what I am plotting is for each of those angles, what ratio did I get for them? When you do that, the intervals that I selected for the scale was going by pi over 2 or 90. So to do all of those 45s, I'm just graphing them halfway in between. So I didn't label all those. We didn't need to have the tick marks be that frequent, but it'd just be halfway in between. So I'm going to keep going here. So at 45, halfway in between 0 and 90, that would be up at 0.7, square root of 2 over 2. Then 90 was 1. 135, square root of 2 over 2. 0, negative square root of 2 over 2. Negative 1. Negative square root of 2 over 2, and then back to 0. Now, what I'm going to have you do once you have all these points plotted is go ahead and connect them with a smooth, continuous curve so we can see what our picture looks like. And I'm going to go ahead and put an arrow on the end over here and over there. And remember what the arrow means. It means the graph continues, so it's going infinitely in both directions. Now let's talk about what this graph is saying to us. So first of all, is it a function? If we do the vertical line test across this graph and I pass a vertical line anywhere, it would only touch one, so it's definitely a function. So when we say sine function, this is why the graph is a function. It's continuous. If you remember what I mean when I say continuous, no breaks. So there's no places in the domain that are excluded, so we have no excluded values. So the domain is going to be all real numbers. We can pick any angle we want, then in other words, and we have this smooth continuous curve. Now I want you to highlight. If you have a highlighter, this is sometimes helpful to look at it from a highlighter. I'm going to have you start at 0 and highlight out to 2 pi or 360. That highlighted region then is our parent graph. So what I just highlighted is the parent graph for sine. So couple things to note about the parent graph if you can make these points bold for yourself. The 0, 0. It starts in the middle of the graph, so it's halfway between its max and its minimum. It's starting at that middle. It goes up to a maximum. So these are like the critical points that I would be most concerned about knowing when I graph this. And then back to the middle. At 180 it was 0. Then to our minimum, which is happening at 3 pi over 2 or 270, and then back to the middle again, that midline of the graph. So those 5 points are what we would consider the critical points of this parent graph that we should know where things are. If you notice, the distance from the middle up to a max or the middle down to a min is the same. It's both 1 in the parent graph, and that will always be the case. They'll always be equal from the middle to the top or the middle to the bottom in this graph of sine. So let's talk about how long does it take to get through this graph? So before it repeats itself. So what I can see on this, my whole picture is it starts at negative 360, you get one of them, and then you get a complete another cycle. So what these are called are periods or cycles. The how long does it take to get through one complete graph? This highlighted portion is 2 pi long. So it goes from 0 to 2 pi, or if you'd prefer in degree world, 0 to 360. That's how long it takes to get through one complete cycle or one complete period. It's another word that they would use out of the graph. So these are called cyclic or periodic functions. They go through the same set of values over and over again. They just repeat and repeat and repeat. And the length of time it takes to get through one of those is called the cycle or the period. So how long does it take to get through a complete graph? So sine just continues to do this over and over again because every time you go around the unit circle, you go through the same set of values again. So it's that coterminal idea. There'd be infinitely many places and infinitely many repetitions of this picture. So starts at the middle, goes to the max, middle, min, and middle. That's the parent graph for sine. Okay, we're going to do the same exact thing now for cosine of x. So go ahead and let's get everything labeled here. Y equals cosine of x. So our x-axis is our angle measurement. Our y-axis is our ratio. And again, we're going by 90 or pi over 2 intervals. So I'm going to go ahead and have you just plot the points. So you can pause the video if you want to do that. So go ahead, start at your negative 2 pi, and go ahead and plot your points. And again, those square root of 2 over 2, I'm just guesstimating those to be about 0.7. So you can pause or you can kind of plot with me here. So we're just doing the exact same thing we did for sine. So if you don't know what something looks like, make an XY chart and go ahead and plot. So we're going to connect with a smooth continuous curve. I'm going to go ahead and stop the graph. I'm not going to do arrows yet because we'll talk about that. If you do the smooth continuous curve, notice again, vertical line test, it is a function. It's continuous. There's no breaks. So it looks really similar to the sine graph that we just did because our sine and cosine values are always going to be basically the same set of numbers. It's just when we do our reference angles, so say like the sine of 30 is a half, the cosine of 60 is a half. We have that cofunction idea, the opposite and adjacent flip. But basically, the graphs are going to go through the same set of values, just in a little bit different ordering, I guess, from where it starts. Now, let's take a peek at what happens at the ends. Now, at 2 pi, it's at its maximum of 1. If I did the next value, which would be pi over 4 past that, would be at square root of 2 over 2 again, it would be going down. So this is a really important idea. But this graph is going to continue, but it's going to be going down from there. Please don't make it look like a parabola. It doesn't continue to grow. It bounces back and forth between -1 and 1. So it would be decreasing there. And then same thing at the other end, that would be a decreasing number. So I'm going to go ahead and make sure those arrows are going down. So grab your highlighter. Let's go ahead and highlight our one complete period. So the one that people usually talk about is starting at 0 and going to 360. So very similar to what sine does. And let's go ahead and mark the most important points, the critical points. Starts at a max. And then at 90 it was 0, so it's in the middle. Goes down to the minimum at pi, -1. Back to the middle at 270, and then up to a maximum. So cosine starts at a max, then middle, min, then middle, then max. So it goes through that cycle of values. So that is the parent graph for cosine. So that's what we're going to base all the other transformations off of. A complete cycle then is exactly the same as what it is for sine. It goes from 0 to 2 pi or 0 to 360. If you want to use degree world here. It takes 360 or 2 pi to get through one complete graph. Think of it as once around the unit circle to get through all the values for cosine. So again, it repeats over and over again. Now, I want you to take a look at the two graphs when they're graphed together. So I have that on the bottom of your next slide, so you can take a peek at that too. We'll talk about this. I graphed the sine in blue and the cosine in red. So when you're looking at the pictures on here, look at the two graphs and let's talk about what's similar. They have the same max and min, so 1 and -1. Basically, the graph looks exactly the same except for what? What's the difference? What's the transformation? And it's right here, the shift. It looks like they're one interval or one tick mark, which happens to be 90 degrees or pi over 2 apart. If you slid this cosine graph 90 degrees over, it would line up exactly with the sine graph. And I want you to think about why that is, this idea of cofunction, why we call them sine and cosine. Cofunctions are where in a SOHCAHTOA triangle, that 90 degree or 30, 60, 90, 45, 45, 90, whatever it is, right triangles, the other two angles besides the right angle always add up to 90 degrees, right? So think about a 30, 60, 90. The 30 and the 60 always add up to 90 because the other angle in the triangle is that right angle. So we only have 90 degrees left for the other two. So the two other angles in your triangle are always adding up to 90, which is why this graph has a 90-degree shift. Because whatever your reference angle is you're doing for sine, cosine would be 90 minus that other angle, right? Because they're the other two angles in the triangle. So if you had 30 degrees, then the other angle would be the 60 or the opposite and the adjacent flip-flop. So that idea of cofunction or 90 degrees apart, that's coming from those other two angles in the triangle, always adding up to 90. So the graphs are basically identical. They just have a 90-degree shift. So they go through the same set of values as the other one does. All right, so let's talk about and kind of fill in what we know about these graphs and now that we've graphed their parent graphs. So the domain values, that would be the x values. That's your input. Those are the angles. So remember, when you think domain here, you're thinking angle measurements. The angles, the arrows tell us it can be anything we want. It's continuous, doesn't stop, it's cyclical, it's periodic, however you want to say that. It's all real numbers. You can use any angle measurement you want, positive, negative. They don't have to be all special values. They can be decimal values. You could have like 27.8 degrees. That's totally fine. You would need a calculator to do it, but we could definitely get that value. So it's continuous, all real numbers. You can pick any angle you want. The range or the output, the y value, those are the ratios. Now let's take a look at your graph. The maximum value that either of these graphs reach is +1. The minimum value is -1. So the ratios, remember we did this in a unit circle, will always be between -1 and 1, inclusive. So brackets on the end there, it includes the endpoint. So the most it can ever be is 1 unit away. Think about our unit circle. That's what we talked about before. And then period. What does a period mean? A period means the length of a cycle. What does one complete cycle look like? How long does it take? So we talked about this. It's starting at 0. Before I repeat it again, if I go to 2 pi, I will get every value exactly once. If I keep going, I'll start getting the same values I had initially. So the period for each of these is 2 pi. And if you prefer in degree speak, that would be 360 degrees. So you can decide what way is easiest for you to think that through. So for sine and cosine, kind of basic information, we know what the parent graphs look like now. The domain, the input, anything we want, output -1 to 1, and the cycle or the period, how long does it take to do the parent graph, is 360 or 2 pi. So those are the basic graphs that we're going to be moving around. So on the next 3 sections or so, we're going to take these parent graphs and we're going to do all the transformations that you guys did with any other parent graph. So we're going to translate it up and down. We're going to move left and right. We're going to dilate it where we stretch or compress. We're going to reflect it. All those places you put numbers in your original other parent graphs will have the exact same effect on these graphs as well. The other thing we need you to still be able to do is identify then where these functions take on certain values. Because of the idea that they continue in both directions, it's going to cause us a little bit of thought as to where these numbers are actually going to happen. So let's talk about a couple of these examples because this will be part of what you're going to be doing for the assignment today. We're not really going to graph anything on this first day. We're going to be looking at what values happen, and then we'll get much more into the graphs tomorrow on our 6-4 lesson. So when is cosine equal to 1? And remember what theta is. It's a kind of our universal symbol for angle measurement. So they could have written this as cosine of x equals 1. That would be the same question. So it's still the angle measurement that you're trying to find. So that's what you're looking for. So when is cosine 1 is the question. I want you to go back to your graph for a second for cosine and take a look at this. There's a few places I can see where cosine is 1 from looking at this graph. So cosine is 1 here. Cosine is 1 there. Looks like cosine is also 1 there. There's 3 places just on the ones that we graphed where cosine is 1. But guess what? Look at the arrows on the end. It keeps going. So how many places is cosine going to be 1? Well, infinitely many. There's going to be infinitely many places. So how do we write all of them? I can't possibly list all of them separately. So I have to have a kind of a concise way of doing that. So this is how I think of it. The first time it happens starting at the y-axis is right at 0 degrees. It doesn't happen again for another 360 degrees. And then would happen another 360 degrees later than that. And it happens 360 degrees before that. So when we write it, and we've done this before, we talked about it when we did coterminal. If I want to say all the values for theta, it starts at 0 and it will repeat every multiple of 360 before and after that. So plus 360k, where k is an integer. Now this is a little redundant because technically 0 degrees is included in this 360k spot because k are all the integers and 0 is one of the integers. So you could say just 360k because 0 is included in that list for k. So you could just say that. Some people like to do angle plus 360k. It just makes them more comfortable. It's just a little bit redundant. So you don't have to have it because 0 is an integer as well. Or if you want to do this in radian land, that would be 0 radians plus all the way around would be 2 pi k. Or again, redundant, you could just say 2 pi k. I'm saying or because you don't need to have both, but you need to understand that both of them are true, so it can be in degrees or radians. So when it says find the values of theta, and it's not limiting your domain at all, our domain is infinite. So that means we're going to have infinitely many places because this cycles. You keep going back and forth over the same numbers. All right, so let's try one more of those. Find all the values of theta, so again, the angle, for which sine is a half. So when is sine a half? Well, when does that happen? Think of your special values here. Sine is a half at 30. We'll do our radian lingo here in a second. When else? So I'm going to go back to the sine graph here for a second. Sine at 30 degrees is a half. So I'm going to put that in there. I know it's not a tick mark for it, but 30 degrees would be about right there. So sine is a half at 30. So it looks like it's also a half right over there, which would be what angle measurement? Well, it's a reference angle of 30. So 30 degrees before 180 would be 150. So 150 is another place where that's going to happen. So it's also going to be at 150. And in 0 to 360, those are the only places where that occurs. It happens in those two locations. It doesn't happen at 210 and 330 because those would be negative 1/2, right? That's below. So the only two that we have are here and here. Now, when are they going to repeat? Well, they're going to repeat 360 degrees later, 360 degrees later, 360 degrees before, and it keeps happening infinitely many times, but it's happening every 360 degrees. So again, just like we had up above, we would have to say plus 360k, where k is an integer, for each of these because there's infinitely many places where it's going to happen. So we say when's the first time it occurs and then everything coterminal with it. So if you just think coterminal when you do these, it's exactly the same thing because that's what the graph is saying as well. It's periodic. All right, or our radian world. So again, equivalent statement in radians. 30 degrees would be pi over 6, and then 360 is 2 pi k. Or, let's see, 150, what would that be in radians? Well, pi over 6 again, and how many 30s do you need to make 150? That would be 5. So 5 pi over 6 plus 2 pi k. So when we're looking at writing out these values and solving for what we need, we're really thinking about that idea that they're coterminal. It cycles. We keep getting those values over and over again. So our big ideas for today, know what these two parent graphs look like. Thinking about what that value is. Should write this in, I guess. The period is the length of one complete cycle or picture. All right, so know what those basic two graphs look like, and then be able to do, like I said, being able to figure out what are those values, and we're really going to focus on the values today, the graphs tomorrow. So our assignment, and we'll take a peek and make sure that everybody can go through and do the review questions as well. Don't forget about the review ones. We need to be able to have some of those getting ready for the final, but know the parent graphs and then be able to say what the values are. So thinking about coterminal to help you with that.